In this video, we're gonna talk about maxima and minima for function of two variables. So the picture that you see is gonna be the graph for the function z equal to fxy, and you see that you have a peak at this point and the peak at this point, and that peak will be the point that more than every point near that point. So when you have a peak like this, in math, we're gonna call this guy relative maximum. Okay, so you see in this case that you have two relative maximum. And also you see that you have on the other side, you have the lowest point of the function here. And this guy turned out to be relative minimum. Okay, so this one will be the definition for the relative maximum and the relative minimum. So it's gonna be the point that higher than the other point near that point, and relative minimum turned out to be the point that kind of lower than the point near that point. Okay, the way to determine the relative maximum and the relative minimum, so you're gonna find the first partial derivative. So if you find the partial derivative with respect to x, so you have y is a constant, you're gonna see that if you have the tangent line like this, the slope of this tangent line turn out to be equal to 0. Similarly, if you find the partial derivative with respect to y, okay, so I have to find something like a parallel to the y-axis like this. You see also that the partial derivative with respect to y at the peak here turn out to be equal to 0. So that leads us to the rule number 1. So the relative maximum and relative minimum at AB happen when AB satisfies the equation, the partial derivative with respect to x and the partial derivative with respect to y are both equal to 0. Okay, so this one will be the thing that we gonna use to determine and relative maximum or relative minimum. And we're gonna define the we're gonna give the name of this point AB that satisfy fx at AB equal to fy at AB equal to 0, the critical point. So the critical point turned out to be the point where you have both partial derivatives are equal to 0. So this one is similar to calculus 1. If you recall, the critical number in calculus 1 turned out to be the number where you have f prime c equal to 0. Okay. And you're gonna talk about a saddle point. A saddle point is gonna turn out to be the point that you see here, that you have the both partial derivatives. So you have the partial derivative with respect to y equal to 0, and you have the partial derivative with respect to x, okay, is also equal to 0. So this guy is going to be the point, which is the critical point. However, it's not going to be relative maximum or relative minimum, so it's not going to be a peak like before. So this one is going to be relative max, and this one is going to be relative min. And in this case, the picture turned out to be look like a saddle on a horse. Okay, so it's gonna be look like a saddle on a horse like this. So we're gonna call this point. Okay, so the point that I'm gonna put here, so it's gonna be saddle point. So this point turned out to call a saddle point. Okay, so this one will be three kinds of point that we gonna determine: relative maximum, relative minimum, and the saddle point. Okay, the two that we gonna use to determine relative maximum, relative minimum, and the saddle point turn out to be called the second derivative test. The second derivative test here is important test that allow us to determine relative maximum and relative minimum. And the second derivative test use second derivative. So we have z equal to fxy is going to be the function that has continuous partial derivative fxx, fyy, and fxy at all point xy near the critical point x0, y0. And you're gonna let a to be fxx at x0, y0, and b to be fyy at x0, y0, and c will be fxy at x0, y0. And you're gonna let d to be ab times a times b minus c square. So you have d equal to a times b minus c square. Okay, and you're gonna check the sign of a and d. So you're gonna check the sign of a and d. So if you have d positive, okay, and a, let me highlight d, okay, with the green color, and I highlight a. So if you have d positive and a negative, the function will have relative maximum. Okay, so we have relative maximum at x0, y0. And when you have d positive, a positive is going to be relative minimum at x0, y0. And if you have d negative, the point x0, y0 turn out to be a saddle point. Okay, so if you have d negative, it turns out to be a saddle point. And if you have d equal to 0, you have no conclusion about extremum at x0, y0, and you're gonna need to do other kind of analysis in order to determine. Okay, so we're gonna have all example for 1, 2, 3, and 4 after this. So for this function, you have fxy equal to 1 minus 2x squared minus 3y squared. So if you like to determine relative maximum, relative minimum, and saddle point, the thing that you're gonna do is gonna be you're gonna find the critical point. The way to find the critical point will be, it's gonna be several steps here. I'm gonna do step by step for you. The first step is, okay, so the first step is you're gonna compute fx and fy, and so for critical point. So you have fx, okay, so you have fx is going to be negative 4x, and fy turn out to be negative 6y, and you're gonna let both of them equal to 0, and you're gonna solve for x and y simultaneously. So you would get x equal to 0 and y equal to 0. Okay, so the conclusion here will be 0, 0 is the critical point. Okay, so you have 0, 0 is the critical point. The second step will be you need to compute the second derivative. Okay, so for the second step, you need to compute the derivative fxx. So fxx will be negative 4, fyy will be negative 6, and you have fxy. Okay, so you have fxy to be equal to 0. Okay, so derivative with respect to y of fx, you have no y left. So you have fxx equal to negative 4, fyy equal to negative 6, and fxy equal to 0. So this allows us to have d equal to negative 4 times negative 6 minus 0 square. Okay, so this one, let me write down the formula for you for the first time. So it's going to be fxx fyy minus fxy square. So you have negative 4 minus 6, and you have minus 0 square. So it's going to give us 24, and 24 is positive. Okay, so this guy is the green color that we highlighted earlier. So this one is the green guy equal to 24. Okay, and you have the yellow guy fxx. Okay, fxx is equal to -4, so it's negative. Okay, so in this case you go to the second derivative test. So you are in the case that D positive, A negative. So this one will give you relative maximum. Okay, so the conclusion here is gonna be, okay, so the conclusion here, this one will be the third step. So it's gonna be 0, 0 is a relative maximum. Okay, so it's going to be relative maximum. Okay, so that will be from the second derivative test. And you have, it's going to be if conclusion, it's going to be if has a relative maximum at 0, 0 with the value equal to f 0, 0. So it's going to be 1 minus 0. So it's going to be f0, 0 equal to 1. Okay, so that will be the conclusion for this one. Okay, so this one will be about how to determine relative maximum, relative minimum of the function. So this one kind of easy to do. So this one is the fourth step for the conclusion. Okay. Let's do one more. You have fx equal to x squared plus 2xy plus 2y squared minus 4x plus 8y minus 1. Okay, so for this one, again, you have the first step. The first step turned out to be you like to find fx. Okay, fx is going to be 2x plus 2y. Okay, and you have minus 4. 2x plus 2y minus 4. And you have fy equal to, okay, so you have fy equal to 0 to x, okay, and you have plus 4y plus 8, okay, so this one will be this guy equal to 0, equal to 0, equal to 0. So you would get x plus y equal to 2, and you have x plus 2y equal to -4. Okay, so you have x plus y equal to 2f plus 2y equal to -4. So you're gonna solve for this system for x and y simultaneously. So you would get 1 subtract 2 or 2 subtract 1 would be nicer, right? So this guy is 2 subtract 1. So it's going to be y equal to -6. And you're going to plug into the first equation. And you're going to obtain x equal to 8. Okay, so you get x equal to 8 and y equal to -6. So you have the critical point, which is 8, and -6 is the critical point. Okay, so you have 8 and -6 is the critical point. So this one is the first step. The second step, we're gonna compute Okay, so we gonna compute fxx. Fxx, you're gonna dip with respect to x, so you get 2. Okay, fyy, that would give us 4, and fxy, okay, fxy, you differentiate, you get 2. Okay, so that will be your partial derivative, second order. And so you compute d equal to fxx fyy minus fxy square. So it's going to be 2 times 4 minus 2 square equal to 4. Okay, and this guy will be positive. Okay, so you have d equal to 4 positive in this case. And you have fxx equal to 2. Okay, so this would be also positive. Okay, so in this case, you would get, okay, so you would have to have a negative 6 is relative minimum. Okay, so is a relative minimum. Okay, so you reach this conclusion. So this one is the third step. Okay, and finally we gonna have the fourth step, which is you have f has a relative minimum at a negative 6. Okay, with the value if a negative 6 equal to, okay, so you just plug into the original function, and if you plug in correctly, you would get negative 41. Okay, so this is how we determine relative maximum or relative minimum value, and it's turned out to be relative minimum in this case. So you see that it's gonna turn out to be first step, second step, third step, and the fourth step. So it's gonna turn out to be 4 steps in order to reach this conclusion. Okay, so you see we have the d is a constant for these 2 examples. We're gonna have d which is not a constant in the next example. You have if xy equal to y cubed minus x squared plus 6x minus 12y plus 5. Okay, so you're gonna find critical number for me. So the first step, you're gonna have fx. Okay, so you have fx equal to negative 2x plus 6. Okay, so you have fx equal to negative 2x plus 6 and fy equal to 3y squared. Okay, derivative with respect to y minus 12 equal to 0 like this. So you would get x equal to 3. Okay, so you have x equal to 3 and you have y equal to, so you get y squared equal to 4. So don't forget that you would have 2.2 or negative 2. So we have 3, 2, and 3, negative 2 are critical point. Okay, so it's gonna be, you have 2 critical points in this case. Okay, so that's our first step. The second step will be, so you get the second step, so you have fxx, so we're gonna compute fxx, so we compute fxx, so you get negative 2, fyy, so you get 6y, okay, and you have fxy turned out to be 0, okay. So you have d, which turned out to be the function in x and y. You not see variable before, but now you see it will be negative 2 times 6y minus 0 square, okay, and this guy will be negative 12y. So you have the xy equal to negative 12y. So the third step, we're gonna analyze both critical point. So for the third step, okay, you're gonna kind of drawing a table. So normally I'm gonna teach you in the way that you have the critical point. Okay, so you get DAB. So let me draw some table for you to see what's going on. So you have this one, and we're gonna have DAB, and you have FXXAB, okay, and you have the conclusion, and so the value. Okay, so you're gonna draw this kind of table. Okay, so you have the critical point, you have D, you have fxx, and conclusion, and you have the value. Okay, so in this case, for the critical point, you have two critical point, 3, 2, and 3, negative 2. So you put them into our table, and you compute D at that point. So you have D at 3, 2. So it's going to be negative 12 times 2 equal to negative 24. And you have negative 12 times negative 2 equal to 24. So this guy is negative, this guy is positive, and you have fxx, okay? So first of all, you see that the positive case is here, and you have fxx equal to negative 2, which is negative, okay? So it's going to be negative in this case. And you see that this one, you have fxx, d equal to negative value. So let me highlight with other color. So in this case, if the negative, so if the negative is turned out to be saddle point, okay, so if you have the negative, it turned out to be saddle point. So you don't need fxx, so you can conclude that this guy will give you saddle point automatically. Okay, so this guy gives you saddle point automatically. And if you have the positive and the yellow guy, negative, this one will be relative maximum. Okay, so this guy is going to be relative maximum. Okay, so when you have the saddle point, you don't need the value. Okay, so you don't need the value because it's not going to give you the peak at all. So you have relative maximum, and you compute the value f at 3, negative 2 for me, and this guy turned out to be 30. Okay, so that will be you just plug into the original function and you obtain the solution like this one. Okay, so this one will be the table in the third step. And finally, at the fourth step, okay, so at the fourth step, you're gonna conclude that if has a saddle point at 3, negative 2, and f has a relative maximum at 3, 2 here, and 3, negative 2 with the value if 3 negative 2 equal to 30. Okay, so that is gonna be the conclusion, and it's gonna be the whole thing for this question. Okay, so you see that it's gonna be 4 steps. 1, 2, 3, 4. The first step, find the critical point. Okay, so the first step is finding the critical point. The second step, compute D. Okay, use the second derivative. And the third step, you draw a table like this one to determine whether the critical point that you have in the first step turn out to be saddle point, relative maximum, or relative minimum. And the fourth step, you give me the conclusion for the point that you are having here. Okay, so this one will be 1, 2, 3, and 4 step that we have for the question that we have. Okay, so I'm gonna stop here, and I'm gonna do more example D, E, and F in the next video. Okay, so that you're gonna see more example. So this one is going to be just the introduction to the second derivative test. Okay.